for this topic, and it all started with Rauch and Tremaine's paper. Well, much of what is being discussed here started with Rauch and Tremaine's paper in 1996, where they showed that the relaxation of stars in near-Keplerian potential is mostly driven by secular effects, not by the two-body relaxations, dynamical two-body relaxations, scattering, but it's due to secular effects. And Jihad rightly praised this paper for covering many of the topics that people are thinking about these days, and it has many statements which I don't understand. And one of the statements is also about the secular friction. So by fluctuation dissipation theorem, whenever you have fluctuations in the system due to some mechanism, typically you also have dissipation. So this paper says something which I don't understand. And with Anne-Marie Madigan, we decided to explore this aspect a little bit. So the physics motivation for this is that, let's see if I can. Should I be pushing on something? This one. Okay. So the physics motivation, of course, is to ask a question whether the secular friction, which causes the secular eccentricity drift, is also a much stronger effect due to traditional two-body scattering, but this is a faster thing. And then there are astronomical motivations, so it's important for inspiring IMBHs and galactic nuclei, and there were some experiments done by Baumgart and Simon and Alessia Golandris, and also very nice experiments by Matsubayashi et al. In 2007, where they saw what happens to eccentricity of inspiring IMBHs. And they saw that it was quite erratic, sometimes growing to high values, sometimes not growing to high values, until you get to the stopping radius, where the mass of the IMBH becomes comparable to the mass of the stars within that radius. And then the eccentricity grows quite dramatically of the IMBH. And Matsubayashi explained it very well. So the explanation is very simple. Once the IMBH begins scouring this core, which I show here in white, you can see that any eccentric orbit experiences drag at the upper center, and this drag increases its eccentricity. So you see a dramatic increase of eccentricity in the simulations once you get to this radius, okay? And that's actually explained quite well, I think, by the traditional Chandrasekhar dynamical friction type argument. But of course, it's also interesting to ask what happens before you get to the stopping radius and whether there is some substantial secular friction which drives the eccentricity. Okay, so then I have been talking to Rainer Schödel yesterday. Rainer said, I'm going to be bored at your talk. I'm not going to understand anything because it's not relevant. So I tried to make it relevant. Okay. So the first, there is, I think, very strong astronomical motivation to consider this. So for example, in none of the talks have I heard, I mean, most of the talks have equal mass stars, right? But if you have heavy stars, black holes, and you have light stars, do you also expect some segregation in the eccentricity space due to the secular dynamical friction? So we don't know. This could be important. If, for example, all stellar mass black holes by some collective effects congregate to high eccentricity, low angular momentum orbit, this could be very important for embryos and for tidal disruptions. Okay. And then there is this whole issue of IMBH, possible IMBH in the galactic center. This is not the most popular theory right now, but I think we have to be a little bit open-minded. If IMBH indeed inspired several million years ago in a galactic center, it would first of all result in a dramatic burst of ejected stars. So all these high-velocity stars would come from the inspiring IMBH. And if IMBH is eccentric, this ejection is not isotropic, but in fact it comes out as a kind of broad jet, mostly in the plane which is close to orbital plane. And because the IMBH is precessing, the jet is rotating on the sky. So if you plot the number of stars which is being injected into the visibility, say Gaia visibility domain, this is modulated by the precession of the eccentric black hole orbit. So I think it's potentially quite interesting. Another interesting consequence is if they use IMBH to deliver young stars to the center of the galaxy. This was suggested by Hansen and Milosavljevic. You have very interesting effects on the stars which are being stripped from this IMBH. So in particular, you see that if you plot the inclination of the stars, then most of them, this is for the eccentricity of IMBH orbit of 0.6. Most of the stars are concentrated near the inspiral plane, so this is inclination near 0. But there is a wide spread, and just like Gonchi Lee showed for planets, the same effect happens for the stars which are being stripped from the eccentric IMBH orbit. So due to the same eccentric quasi-Lidov effect, the stars get flipped, and you have a broad distribution of eccentricities. And I want to know that this is exactly what you see in the galactic center. Okay, some of the stars are in the disk, and some of the stars have crazy inclinations, and they have nothing to do with the disk. Okay, so this is in fact a compact dynamical explanation. There are arguments why this is probably not favored, but I think this diagram is worth to keep in mind, and the eccentricity of the black hole plays a key role in this scenario. I did not include GR precession. Sorry. Okay, so now I want to talk again. Rainer, you have to wake up. This is pretty pictures. Okay. Stop looking at your phone. Thank you. All right. So okay, now I want to get very conceptual. So this is like, I don't know if this is right, but I want to draw for you a cartoon. And I want to start with the IMBH, and this is IMBH's orbit. Okay, so I'm going to represent IMBH's orbit with this big circle. Plus means that it has a positive angular momentum, okay? And because it's in the potential of the cusp, it is precessing in the backward direction here, all right? Now, and I also want to consider a star which has negative angular momentum. That means it's precessing in the positive direction, prograde relative to the IMBH's orbit. Now, I want to say that when these two things come close to each other, there is a strong secular encounter. So this is not a weakly perturbative regime. There is a strong secular encounter, and it randomizes the orbital orientation of the star. So now it's precessing in the random direction. And the net angular momentum of the IMBH has decreased, right? So if you go from here, this is a big plus. Okay, after the collision, this is reduced. Okay, if you start with a star which is precessing in the opposite direction, when it collides secularly with the IMBH, again, its orbit randomizes, all right? And this increases the angular momentum and decreases the eccentricity of this black hole. Okay, so now if you consider a collection of orbits, right? So this black hole is now in the cluster of stars. So some stars are precessing in the prograde direction, some stars are precessing in the retrograde direction. The exchange, once the stars encounter the black hole, their orbits get randomized. They exchange angular momentum with this black hole. Okay, but because this black hole is precessing backwards, it encounters more of the minus stars than of the plus stars. And I'm talking about secular encounters. So because it encounters more of these guys, it should actually increase its angular momentum. And as a consequence, it should decrease its angular momentum. And as a consequence, it should increase its eccentricity. All right? So this is a prediction. And this is a prediction that means that if you now artificially reverse the direction of precession of this black hole, so you just go in by hand in your code and you change the direction of precession, in fact, its eccentricity should decrease. So the direction in which eccentricity grows or decreases should depend on the direction of the precession of this IMBH. So I'm going to tell you how to test this. All right, now, another prediction is if you have a counter-rotating cusp, so if all of your orbits are counter-rotating relative to the orbit of the IMBH, this black hole only interacts with the orbits with a negative angular momentum, and therefore its orbit, its angular momentum should decrease, and its eccentricity should grow very rapidly. Okay? And conversely, if the cusp is co-rotating, it only encounters pluses, so its angular momentum is increased, and its eccentricity should be decreasing. Again, this is a prediction of this phenomenological picture. Now, you notice that this, if you look at this carefully, you will say this is completely wrong. This cannot be. And the reason it cannot be is that after several encounters, you will create a distribution of, well, let me show you what you create. You create a distribution of preferential orbits. There will be more pluses than minuses. And so by the arguments of detailed balance, you should finally arrive to equilibrium situation where you have no net exchange between these orbits and the angular momentum of IMBH. So if you keep the situation in equilibrium, then this mechanism will not work. However, if you have radial migration, so when the IMBH migrates radially, it encounters new populations of stars, and then because this is a situation out of equilibrium, you can actually let this effect play out. Okay, so one of the predictions of this, so these are all predictions of this picture, and then the final prediction is that it all works only if IMBH migrates inwards. And the faster, the better, because then you have new supply of fresh stellar orbits. So numerical experiments, these are crazy n-body simulations. So all n-body people will faint when they hear what we actually did. But basically, we took the smooth potential of the cusp, which is the parameters characteristic of the galactic center. And the stars precess due to the cusp, but they don't interact with each other. So they interact collectively with the cusp, with the potential of the cusp. Then we controlled IMBH precession, like literally physically rotated the radius and the velocity in the direction that we wanted to test. And this would turn the ellipse of the IMBH. So this is like a rotating bar. So this was controlled. And also, we controlled the inspiral by hand, well, by just decreasing the radius and increasing the velocity vector by the square root of the factor by which we increase the radius by each time step. Thank you. So here are the results of the numerical experiments.
So the stars interact with the smooth potential of the cusp.
Yes.
And with
And with
the intermediate mass.
the intermediate mass black hole. Sorry, of course, the stars interact normally with the intermediate mass black hole. But the orbit of the intermediate mass black hole, it feels, of course, angular momentum exchange with the stars. So its eccentricity evolves according to these interactions. But we control its precession. So it can precess forward and precess backwards. Impulse from the outside. We can test if it precesses according to the equations given by the cusp, but we can also reverse it. And we can accelerate it. We can do whatever we want. Yes?
I'm just curious about the mass and stars in these experiments.
So the mass in stars was chosen so that it's 1 million solar masses up to a radius of 1 parsec for the parameters of the galactic center.
So you'd expect it to be self-gravitating.
Yeah, but we're only considering inner parts of this. So yeah, but that's right. So our black hole, the radius of the black hole is like a little bit less than 1/10 of a parsec. So okay, so basically numerical, I have to say that I wouldn't be giving this talk if numerical results were opposite to these predictions, but in fact they are broadly in agreement, not in detail. So for example, this is the result of each of these lines is an average of 10 runs. So this is the run, for example, with the retrograde precession. This is the correct precession for IMBH. and you see that eccentricity indeed grows. And this is the result when we reverse the direction of the precession. So you can see systematically decreasing eccentricity. So this is one.
What is the initial distribution of the stars?
This is isotropic.
Isotropic.
Yes. This is for
Velocity space, the velocity
everything is isotropic. Yes. So this is just to give you an idea of what's happening to the stars themselves. So remember, I said that this picture will not continue because the stars will flip eventually to impose detailed bounds between different orbits. And this is just the illustration of what happens. So this is the quadrants, octants, sorry, of eccentricity vectors of the stars. The eccentricity vector of black holes here. And you can see that the number of retrograde stars which have the same eccentricity vector and the same quadrant as a black hole is increasing, and the number of prograde stars is decreasing. So this is exactly what this would predict. So you do need radial migration to get some changes. All right, and the demonstration of this is this, right? So this is, again, the normal in spiral, where we artificially impose the in spiral according to Chandrasekhar formula. And this is the eccentricity evolution of the in spiral, which is slowed down by a factor of 10. So you see, if you slow down the in spiral, then the eccentricity of the IMBH does not grow. Okay, and finally, this is the example where you have counter-rotating and co-rotating cusps of stars. So for counter-rotating cusp of stars, you have very dramatic eccentricity growth, and for co-rotating, you have very dramatic eccentricity decrease. And so we've checked that this effect is not due to two-body collisions because we've introduced, I'm almost done, we've introduced softening, which basically suppressed two-body scatterings, and the results did not change, in our numerical experiments. So conclusions. We think that this secular friction is important for IMBHs in the galactic centers. So another thing which troubled me a lot was that it seems that in some situations the torque can be in the same direction as precession. So if you generally, your intuition would say that if you have a rotating bar, that the torque on this bar should be in the direction which is opposite to rotation. We don't find this. We find that sometimes torque is directed in the same direction as rotation of the bar. And that seems to violate some of the things that Scott, Tremaine, and Weinberg said in their paper where they considered general dynamical friction and spherical systems. But I mean, the only caveat to this is that this is a second order perturbation theory argument. And I'm not sure if perturbation theory argument apply to our system because we have very strong encounters between the black hole and the stellar orbits. And we think that these conceptual models, even though there is no, I mean, there are obviously many assumptions, but we think that they give reasonable heuristic explanations to our numerical experiments. So this is it.